So we're going to start chapter 8. We have chapters 9 and 10 also to cover in the next 2 weeks. These are going to be a bit more math heavy. Yay. At least 8 and 10 are. Number 9 is not as math heavy, but it'll be fun regardless. We're finally going to get into some real chemistry with doing reactions and stuff. So, solutions. Okay, so solutions are going to be our last kind of state of matter. We've talked about gases. We also talked about liquids and solids a little bit. And now we're going to talk about solutions, which are kind of where most chemistry is going to happen. So, solutions are going to have at least 2 components. All right, there is going to be a solute, or multiple solutes, and there's going to be a solvent. For example, if we're going to figure out what these are going to be, this is going to be what the solute is dissolved in, and this is going to be what is being dissolved. If we take, for example, salt water, we have the solute is salt, and the solvent is water, right? There's another way to describe the solvent is it's the one that there's a lot more of. In salt water, there's a lot more water than there is salt. So we're going to see that that's going to be also another way how we're going to identify it. Okie dokie. Cool. So again, as always, we're going to kind of just start with vocabulary. So the solvent is going to be the component of your solution that's going to be the most. Very often in chemistry, that's going to be water. Water is what we're dissolving all our stuff in for it to take place, for whatever reaction we want to happen. And then the solutes we're going to see are going to be the kind of bits that are dissolved in it. So, for example, if you're taking sugar and dissolving that in water because you're going to make tea with it or whatever, the sugar is going to be your solute. You're going to have water again as your solvent, and you're also going to have all those compounds in the tea that are also going to be solutes. So you can have as many solutes as you want, but you can only have one solvent. Okay? And there is only one solvent per solution. Very often you're going to see solution abbreviated SOL''N, just so you know. So that means solution. Okay, so you can have one solvent, and you can have as many solutes as you want. You can have one solute, or you could have, a billion of them. Does not matter. Okay. Let's do a couple more examples. Let's say we have some other solutions. Let's say we have air. Air is a solution. We have a solvent and some solutes. We're going to go into those. We also have, how about steel? That's another example of a solution. I want to not only focus you guys on aqueous solutions, that is solutions in water, but there are tons of other solutions that exist as well. So, for example, here's a gas one, air, and a solid one, like steel. Another one, let's say we have, how about vodka? These are all solutions. Okay, so we're going to look at these, and we're going to kind of take a look at their components, and try and figure out what the solvent is and what the solute or solutes are. Okay, so does anybody know what is in air? We briefly mentioned this in the gas chapter. maybe just 3 of the components of air. Yes, very good sample. So air was about 78% nitrogen. We had 21% oxygen and 1% argon with a bunch of other random stuff also. So looking at those numbers, which one is going to be the solvent? Yeah, nitrogen for sure. So our solvent is nitrogen, and the solutes are going to be the other two, right? I mean, it's going to be everything else. Oxygen, and then argon, and then if we had, water in there, and carbon dioxide, and whatever cyanide gas, that's all going to be part of the solutes. So solvent, the big one, and solutes are everything else. Okay, anybody know what steel is made of? Two things mostly. Let's just pretend this is just a very basic steel formula. Let's see. So actually, interestingly, neither of those should be in your steel. Yeah, carbon's going to be one of them, and iron is the other. Yeah, so iron is going to be the... So I have actually no idea what the percentages are, but I'll just make them up. Let's say steel is 90... sorry, I'll go back to black. So if steel is 90% iron and 10% carbon, the solvent is going to be iron, right? The one that's more. There's more iron in there, so our solvent is iron. And then our solute is carbon, and if we have chromium or nickel or whatever else in there, those would also be solutes. Okay, and last one, vodka, our solvent is water. And our solute is ethanol. So we can have all manner of solutions, right? We can have solids that are dissolved in liquids. For example, that would be salt water or honey or anything like that. We could have liquids dissolved in liquids. That would be your vodka example. We could have gases dissolved in liquids too, interestingly enough. So this soda here has little bubbles in it, right? That's carbon dioxide that has been dissolved into water. So we can also have, gases being solutes when they're part of liquids, or solutions rather. Okay, so don't get, not everything is just solid dissolved in liquid, though that is the majority of solutions. There are also other types possible. So we have gas and gas. We had two solids. We had iron and carbon put together. So, yeah, cool. Okay, so that's one thing you should be able to do is take a solution, either one that's very easily known or one that I've given you the components for, and you should be able to tell me what the solvent is and what the solutes are. Okay, any questions on that? Okay, so that is our first bit of terminology. Another very important thing, so the solvent and solutes are going to tell us what's in the solution, but they don't tell us how much is in the solution. So we're going to have several ways to talk about that. And this is all going to be referred to as concentration. Okay, so that's going to be how much solute is dissolved in the solvent. So we have a couple of units for this. We often talk about grams of solute over grams of solution. We can also talk about moles of solute over liters of solution. And another somewhat less common one that used to be used more often was moles of solute over kilograms of solvent. So notice the two on the left both have solution as part of your denominator, but on the right it's just solvent. Okay, we have fun terms for all of these, but these are kind of the big three units that you're going to see when talking about concentration. So again, concentration is how much solute you have dissolved in your solvent. Alrighty, so, whoops, we don't need pastels here. We often refer to this one as something called percent weight per weight. This is a measure that you're going to see often in healthcare. So for example, you know that 0.9%, it's percent W divided by W, percent weight percent, which is also just called weight percent. That's how I'll be talking about it, which is percent W per W. So that's weight over weight. So you see we have grams of solute over grams of solvent. Those are both weights, they're masses, right? There are other ones. You can also have weight per volume or volume per volume. For example, your vodka that you're going to buy at the store will say it's 40% alcohol by volume. That's a, 40 milliliters of ethanol per 100 mils of vodka. That's a volume per volume percentage. However, that's not typically used in chemistry, so we're going to forget about that. Okay, so back to the percents weight per weight. You will see weight percents if you go into healthcare. For example, 0.9% saline is the basis for all your IVs. So anytime you're giving someone an IV drip, that's 0.9% sodium chloride in water, right? You can also have like 5% dextrose, which is 5 grams of glucose dissolved in 100 grams of water, or rather 95 grams of water. And so you'll see kind of those around. If you also see drugs, you'll see that they'll say, like on a cream or whatever, it's like 0.1% of this drug in the whatever ointment that's on there. So you'll see that weight percent fairly commonly throughout your life experience. All right, in chemistry, the biggest one that we use is this middle one. And we often abbreviate this one with a big M, which we call molarity. Okay, which is the moles of solute per liter of solution. This is the most common by far unit in chemistry. However, fairly recently, the kind of board that determines all of what units we use and everything, the IUPAC, has kind of determined that this will now be called molar concentration instead. But I've never heard anyone use molar concentration. Everybody says molarity. So I will be using molarity. So that's just something that's, stuck in my head. So you guys will use it too. And everybody else uses it. All right, the last one, just to confuse you guys, not typically used all that often anymore, but it will be important for a few of our calculations, as well as when you get into Chem 102. So this one is called molality. So very similar word, unfortunately, and it is designated with a kind of cursive M, a cursive lowercase m. And so that is molality. Okay, we will talk about molality in a little bit, but by and large, most of what we're going to use in chemistry is molarity with an R. That's the capital M. Okay, so these are kind of the three concentrations we're going to be talking about. So let's go ahead and do some practice. So let's say I have, let's calculate all three of these, okay? Let's say I have 25 grams of calcium chloride and 75 grams of water. And this, putting it together, you make, 90 mLs of solution. Very often when you put a solute into a solvent and you dissolve them, the volume does not go up as much as you think it will. If you put, a couple teaspoons of sugar into your coffee because you just love sugar, you're going to see that the coffee volume does not actually increase by the same amount of sugar that you put in. You're going to see that the sugar will just kind of disperse throughout and you're not going to have a huge volume change. Okay, so we're going to calculate all three of these concentrations of this particular solution. So we can start with the weight percent. So, and since it's a percent, since I had forgotten to write that, percents, remember, are always times 100%. That's just, you're going to get a decimal when you do it. So if you want to make it into a percent, you multiply it by 100. Alrighty. So if we want to do percent, that's going to be grams of solute over grams of solution times 100%. Which one of these is going to be our solute? Yeah, calcium chloride, right? So that's going to be our 25 grams on top. Now, what is the mass of our overall solution? Yeah, it's 100, right? Because the solution is both the solute and the solvent. It's both components. So that's going to be 25 plus 75 grams. Or as Zoe has already calculated, that's 100. Right? And if we go ahead and do the math, we see that this is 25%. Okay? So notice that grams of solution was the mass of solute plus mass of solvent. If you had multiple solutes, you would add those together, of course, as well. Okay, any questions on this percentage one? Okie dokie. Let's go ahead and do the let's see what Melissa's got to say. That's so the mass of solution. I'll just write that in a nice little formula here. How about in green? So mass of the solution equals the mass Okay, so the mass of solution is equal to the mass of all your solutes as well as the mass of your solvent. All right, so in this case we had one solute, and of course we have one solvent. So we were able to add those together to get the mass of solution, since this particular formula uses the mass of solution on the bottom. Okay, cool. So the molarity, capital M, is moles of solute over liters of solution. Alrighty, so which numbers from this are we going to use from our original problem, our original solution descriptors? Yeah, we're going to use 25 and 90, right? Absolutely. However, both of those are not quite in the right unit so far. We know that we have 25 grams of calcium chloride, and we have 90 ml of solution. Alrighty, so since we need moles of solute and liters of solution, neither of these units is acceptable as is. So how are we going to figure out this? How are we going to change these units? Yeah, for sure. So this one, we can say it's 1 liter over 10 to the third mLs, which gives us 0.09. Here, you're right, let's give it some sig figs. Yes, exactly. And then so for the grams to moles, we're going to have to bust out our periodic tables, or if we're lazy, we just bust over to Wikipedia, and we type in calcium chloride and see what the molar mass is. Okay, it's 110.98. So we know that we have 1 mole over 110.98 grams. There's your hint for your exams in the future. Just Wikipedia your molar mass. It's an easy shortcut for you. Okay, cool. So let's do this calculation. Okay, so that gives us 0.225 moles. Okay, and then if we wanted to find the molarity, then we're just going to divide those two numbers. So in blue, 0.225 mole calcium chloride. Oh gosh, that's the wrong one. There we go. Over 0.090 liters is going to be equal to 2.5, actually just 2.5, yeah, 2.5 molar. Okay, this is typically the unit you'll just see a capital M. That's the same thing as saying 2.5 moles per liter. Okay, those are the same thing. Okay, remember molarity equals moles per liter. So you will see molar, capital M, as a unit. But what that just means is moles per liter. Okay, so it's a conversion factor. It's a concentration. All right, anybody have any questions on that one? Okie dokie. So let's go to our third one now. Let's see if we do the molality. Squiggly M. Remember, that's moles of solute over kilograms of solvent. Okay, so going up again, we are going to use the 25 and the 75 this time, because that's our solute and solvent. So in this case, we already have our moles of solute, right? We already calculated it for the previous problem, so we can just go ahead and use that number again. We found the 0.225. Remember, we had already figured that out. Now, for the kilograms of solvent, if we're going back up here, all we have is grams of solvent. So we're going to have to go ahead and convert that to kilograms. All right. So 75 grams. Remember, kilograms goes on top and gram on the bottom. That's going to be 0.075 kilograms. Okay. So if we go ahead and do that, let's see what this is going to be. 0.225 divided by 0.075. Oh, wow, 3. Okay. we have squiggly m as our unit, or we can say 3.0 moles per kilogram. Same thing. Okay, you can use either unit. They are equivalent to each other. Alrighty, so this is just three ways of calculating concentrations. So unfortunately, these three, the same solution looking at three different units of concentration has given us pretty different answers. And unfortunately, that's just kind of the way it is. So there's nothing obvious to tell us that 25% is 2.5 mole. It just happened to be that. That was kind of lucky. But 25% to 3.0 mole or moles per kilogram, that's even less kind of intuitive. So unfortunately, you will have to, there's not an easy way to convert in between these ones. Okay, any questions on any of these three? Okie dokie. So we're going to move on. Okay, let's talk about solubility then. So we're going to kind of look at how do things dissolve. One of the easiest ones for us to look at is, let's start with sodium chloride in water, salt water, very standard solution. Let's go ahead and see on a molecular level how this works. So, why does the salt actually dissolve in the water? So, we know that salt is normally in its, nice solid form. I'm going to draw the, one of them in first, and then I'm going to draw the other. So you remember that sodium chloride kind of is that alternating sodiums and chlorines. Let's just say green is chlorine and blue is sodium. Okay, but water, as we know, shall be purple. We remember that water is a polar molecule, right? We're going to see that a substance, an ionic substance, will dissolve in water if the attraction between the water and these ions is stronger than the attraction for the ions to the ions. So, let me write that out because I know that that's a lot to kind of get at once. An ionic substance will dissolve if the H2O ion forces / attraction is stronger than the ion attraction. And very often this is the case. We know many ionic substances will dissolve in water. That's why they sometimes call water the universal solvent. Okay, so we know that salt dissolves in water, right? Our bodies are salt water, so we better know that. So we're going to go ahead and look at this molecularly. So if you were a sodium ion, which side of the water molecule are you going to be attracted to? Yes, if you were sodium. Yeah, you're attracted to the oxygen, right? Because you're a positive ion, there's the negative side of water that you're going to want to hang out with. So, let's just say this water molecule is going to go steal this hydrogen. I'm sorry, this sodium. In order for that to happen, that has to be a pretty strong force because we have, solid negative, positive kind of thing going on. And so we need to have that water be strong enough to pull off a sodium ion. And indeed, what happens is, let's see, sodium was blue, yeah? Okay. What this is going to look like is we're going to end up having a lot of oxygens kind of hanging out near this sodium. I'm just going to draw 6 because, forget it, I'm going to lose my hand otherwise. That is 6, good lucky me. And we're going to see that those kind of negatives, the delta negatives within that oxygen, are going to all kind of, I drew them a bit too close, didn't I? Oh well. Those are all nicely attracted to that sodium, right? We've got these partial negatives attracted to a full positive. That's going to be a very happy thing indeed. And we're going to see that that delta negative attracted to full positive is stronger than delta negative to delta positive. So delta negative to full positive, stronger than delta negative to delta positive. Okay, that kind of makes sense, right? The stronger your charges is, the more you're going to be attracted. And so, for example, we have kind of 6 delta negatives surrounding this one positive. That's going to be better than a full negative. All those delta negatives, yeah, I'll write it out, Martha. Okay, let's see. Positive plus delta negative is stronger than delta positive plus delta negative. Okay, so that's full positive. Okay, and we're going to see that plus many so that one ion and a lot of delta or partial charges is going to be stronger than 1 plus and 1 minus put together, which is why that salt is able to dissolve. So all these water hanging around that sodium is really favorable. More favorable than putting the sodium next to the chloride. Okay, so this same thing is going to happen for negative ions, just in the reverse. So instead of the oxygens being around our chloride, we're going to have the hydrogens, right? The hydrogens are the positive side. So here's our chloride. And time to draw a cajillion. You know what, I'm just going to draw 4 this time because forget it. I don't want to draw that many. But you get the idea. I mean, there's not really a exact number. You know, it doesn't have to be 4 or 6 or whatever. That's how much I've drawn. Okay, and so we can see that we have nice things going on between all these positives and the chloride negative. Again, I've drawn them kind of too close, so hopefully you can see all of these happy things. Okay, so this is what's called an ion dipole force. And this is even stronger than hydrogen bonding. So this is our fourth intermolecular force now. So don't be forgetting all of those. So this is what's called ion dipole, where we have an ion and a dipole, pretty obviously from the name there, for once the name actually makes sense. And so that's going to be actually a stronger intermolecular force than hydrogen bonding is. So just like we said up here, so this is the partial positive and partial negative in the top right here. That is hydrogen bonding, right? You have partial positive, partial negative, assuming one of them is a hydrogen. This ion dipole thing is going to be a stronger force. Okay? So, it's a happy, nice force. Everybody likes it. Okay, questions on that? Most likely. Okay, think about it. So again, we are going to be kind of going through this pretty quickly, but hopefully not a lot of this is going to be super new to you. Alrighty. So I'm going to give us now a list of how we're going to know if something is soluble or not. So, I don't remember in the textbook if this is presented in Chapter 8 or Chapter 9, but you're going to have to know it anyway, so I'll just go over this now. So, soluble ionic compounds. Any compound with sodium. Let me write these in a different color, actually, just for emphasis. Sodium, potassium, lithium, ammonium, nitrate, or acetate. So any compound that has any of these six will be soluble. Okay, so anything that has a sodium in it, or a lithium, or an ammonium, or an acetate will be soluble. All right. There's only 3 rules. The second one is any compound with chloride, bromide, or iodide. I'm going to do this part in red, unless it also has silver, lead, or mercury. This is just water solubility. We're not going to talk about solubility in any other solvent in this course. Very good question, though. That is a very, very important distinction. Okay, so how we interpret this second phrase is anything that has chloride, bromide, or iodide will be soluble unless it also has silver, lead, or mercury in it. Okay, so that's telling us that silver chloride is not soluble. That we are going to talk about that, Tiffany, when we talk about molecular compounds being soluble in water. Absolutely. But first I want to kind of go over just ionic things. Okay, and our third one any compound with sulfate, we have some unlesses here, unless it has let's see, calcium. Oh, that's shame on me. Barium, lead, or mercury. We can also throw strontium in there too, but that's less common. Okay, so anything with a sulfate will be soluble unless it has one of those 5 ions with it. So calcium sulfate, insoluble. Barium sulfate, insoluble. Lead sulfate, insoluble. Okay, but let's see. Aluminum sulfate would be soluble. Okay, so anything that's a sulfate that's not one of these things in red will be soluble. Okay, so we're going to assume that everything that is not covered by these 3 rules that I've just gone away from, anything that's not on these 3, we are going to consider to be insoluble. Okay, so we are going to have these rules for things that are soluble, and we're going to just assume that everything else is insoluble. Okay? So, I want us to do a little practice before we go on our break. Okay, so hopefully you've screenshotted this or something, so I can move down and give us some examples. Okay, here we go. Or you know what? Maybe I can do this. Let's see. Let's flip this up. Yes. Okay. I realize it's smaller, but it'll give me more room to do our examples here. So this way we can see our rules right there. Okay, cool. Okay, I figured. Fine. Okay, we'll go back here. So, yeah, no rules, that's fine. You guys can look them up or just have them on your, other notes or something. So again, you're not going to have to memorize these because it's open book. So, cool. Let's see. How about we do... I want you to tell me if these compounds you'd expect to be soluble or insoluble in water. And you know what? Go ahead and name them too, because don't forget naming's important. Let's see. What else is a good one? Okay. Let me make that a little bit nicer for us. Alrighty, first one, barium chloride. Is that going to be soluble or not? I agree. If we want to know why, we look at whichever rule has chlorides involved. That's the second rule. And chlorides are going to be soluble unless it has silver, lead, or mercury. Cool. Great. How about sodium chromate? Yeah, that's going to be soluble also, right? Anything... You just gotta see a sodium, that's all you need. You don't even care about what the anion is. If you see a sodium on there, it's soluble. Okay, next one. Ammonium acetate. What are we thinking, ammonium acetate? Yeah, soluble also. Very good. Yeah, both ammonium and acetate make anything soluble, so you have them both there, you better bet it's soluble. Alright, calcium sulfate. No, indeed. Okay, remember, calcium makes sulfate insoluble. Okay, how about calcium phosphate? Perhaps the trickiest of the lot. What are we thinking? I agree, it's insoluble. And why? How do we know? Yeah, because it's not part of any of the rules, so we're going to assume it's insoluble. And indeed, it is. So, cool. Okay, how about aluminum sulfate? Yeah, it is. Yeah, because sulfates will be soluble unless they have calcium or any of those things, but aluminum is not part of the exceptions, so it will be soluble. Okay, very nice. Okie dokie. So, in that case, let's go ahead and take our break now, and let's come back at 4:35 or so, so about 12 minutes, a little bit extra. Okay? If you have questions, as always, just kind of type them out. I will pause the video and everything, and so we can get that uploaded.